because they're these big communities, you're almost like pushed to attach yourself to one of them and become a string theorist or become a loop quantum gravity person. And I think that is unfortunate. And you could say that we always operate in like a digital universe where if gravity is fundamentally classical, there needs to be a lot more noise in the gravitational field in comparison to the quantum case.
Jonathan Oppenheim, a professor of physics at Oxford, centers his work on a new approach for combining quantum principles with gravity, specifically sidestepping mainstream frameworks like loop quantum gravity and string theory. His research instead focuses on the stochastic coupling between gravity and quantum mechanics. Contrary to the ordinarily trodden path of quantum gravity, which often dominate conversations on unifying quantum mechanics and general relativity, Oppenheim introduces stochastic processes as a new axis for inquiry. What ramifications does this have for prevailing theories? We explore that. Jonathan's expertise extends to quantum information, and he's done plenty of work on the quantum version of thermodynamic laws, like the second law and the third law. Something not explored in this episode, but I can't seem to find it anywhere, is the connection between the classical and the quantum by making an equivalence between imaginary periodic time and finite temperature. This is also known as analytic continuation and is often just proposed as an unphysical mathematical scheme rather than a profound connection between quantum field theory and statistical mechanics. My name is Curt Jaimungal, and I have a background in mathematical physics. And what are you working on these days, and what excites you about it?
Well, we've proposed this theory of gravity, which is meant to reconcile general relativity and quantum theory, and so mostly we've just been working on that. I do a little bit of quantum information theory as well on the side, but at the moment, most of my group is working on the kind of what follows from this classical quantum theory.
You used an interesting word, which is reconcile quantum mechanics and general relativity, or quantum and gravity. Whereas most people, as you know, most of the physics community would say quantize gravity.
Right.
As almost a synonym of making gravity and quantum harmonious. So why do you use that word reconcile and not quantize?
Well, I mean, so, people realized, I guess more than 100 years ago, that general relativity, because it's a classical theory, is incompatible with quantum theory. And people usually will write down the Einstein equations, which have, the stress energy tensor of matter on one side, and then they'll show that it's equal to the Einstein tensor, which is, tells us about geometry on the other side. And they'll say, that in almost every lecture on quantum gravity, they'll say, well, you can't have a operator representing matter in quantum theory equal to some classical number representing geometry in general relativity. So that's usually how it's presented, and the usual statement is that we therefore need to quantize gravity in order to make these two things compatible.
To be clear, classical in this case means what? Definite values?
I mean, that's a good question. In classical mechanics, objects take a definite value. And for example, if I have a particle, it might have a definite value for its position and a definite value for its momentum. I could also imagine that I have a probability distribution of classical systems. So for example, you might imagine that someone's flipped a coin, and with some probability, they've prepared a particle to have a certain position and momentum. And with some other, if the coin comes up, say heads, they'll prepare the particle with one position and momentum. And if the coin comes up tails, they'll prepare the particle to have a different position and momentum. So classical systems don't need to be in definite states. They can be in a probability distribution of definite states. But we imagine that there's a fact of the matter about them, even though we might not know, what values of position and momentum the system has. It does have those values in some way. Whereas a quantum system, the main thing about a quantum system is it doesn't even, a particle never actually has a definite position and momentum. So that's the one way to see the difference.
Is that a controversial statement? Because there are different quantum theories or interpretations of quantum mechanics where they do. It's just that the wave function represents our knowledge, or they're hidden variable theories.
Right. I mean, so one of the most famous and I think most important results in physics is Bell's theorem, which essentially says that at least if you have a local theory, then the particles don't have a position and a momentum. So I think most physicists and most of the lay public is used to Heisenberg's uncertainty principle, which says that we can never know a particle's position and momentum at the same time. And what Bell's theorem says is it goes one step further. It says that the particle doesn't even have a position and a momentum until we measure it. Now, that assumes that there's a slight caveat to that. You can imagine a theory which is very non-local, which somehow keeps track of the particle's position and momentum. But I think most physicists don't believe that such a theory makes a lot of sense. And so I think most physicists have accepted the fact that the particle doesn't actually have a definite position and momentum.
You once said that quantum mechanics or quantum field theory comes with plenty of ontological baggage. Yeah, what do you mean by that?
Well, I guess I've described myself as a quantum mechanic with a lot of ontological baggage, and the term actually comes, I think, probably coined by Lucien Hardy, who essentially says that he proved some results which essentially say that if we want to have a hidden variable theory, then the amount of information that we need to somehow have the amount of information that we need to keep track of becomes incredibly large, becomes infinite. So any sort of a hidden variable theory, which describes quantum mechanics, needs to keep track of a huge amount of information, and he calls that ontological baggage. And it's one of the reasons that people tend not to like hidden variable theories. They're rather unwieldy. They have to be non-local. They need to keep track of an infinite amount of information. And so it's much easier just to believe in quantum theory.
I recall Nima said that, I'm unsure if it's Nima, but someone said that even in general relativity, you don't have knowing anything with arbitrary accuracy, because if you were to know something with like infinite accuracy, you'd have to store that somewhere so that information would carry with it energy, and that would create a black hole.
I mean, in some sense, because if you believe in the continuum, then in some ways, any particle has an infinite amount of information that's required to really store the information about a particle. But when we perform measurements, we tend to think of our measurements as being relatively weak and not containing, they don't reveal to us all that information. So we're always somehow operating in a kind of an approximate landscape where we don't keep track, or we don't even learn. For example, we don't learn the position of a system to arbitrary accuracy to an infinite number of digits. We just learn about it to some small number of digits. So in some sense, you could say that we always operate in like a digital universe where the amount of digits that we keep track of is not infinite, but it's some finite precision.
Now, a popular topic these days is the simulation hypothesis. And so when you say digital physics, you just mean that there's something discrete about it rather than simulated.
Right. I mean, physicists often consider like a discrete space versus a continuous space, which has just a finite amount of information. And there's a question about whether that is good enough and is equivalent. Do we ever need to consider systems which are infinite dimensional and have an infinite amount of information? Mm-hmm. That's actually a popular topic right now in, for example, string theorists now are spending a lot of time looking at von Neumann algebras and, can we actually in a field theory really define in a nice way the entropy of a system, because that actually, in the continuum is really difficult to define. So in physics, we tend to mostly think that we can describe things with just finite precision and not worry about the fact that, really these are continuous systems which really require an infinite amount of information to describe properly.
Yeah. Nicholas Gisin also had this argument about there not being a continuum, because he said, look, let's imagine the electron's classical or just some particle. If it's characterized by a real number, then most of the time, most real numbers are not computable, and they have an infinite amount of, okay. But then that would mean that the particle would carry with it that information. And what does that mean, that the particle would carry with it that information? It just is. The particle just moving along. It doesn't have a coordinate We don't think that it carries with it. It chooses a basis to describe itself with coordinates.
Right.
So what's exactly meant when someone says that in a continuum, a particle would have infinite information carried with it?
Does the particle carry an infinite amount of information and I just can't know all of it, or I can only know a finite amount of it? Or does it actually just have a finite amount of information and that's all I need to describe it? And I'm not sure that as physicists we would necessarily make a big distinction between the two cases. If we can't measure and if we can't measure and learn, its position to arbitrary accuracy, then does it have a position to arbitrary accuracy? I don't know, but
Yeah, you mentioned the word philosophical there. What role does, and Lucian Hardy, I believe, is a physicist, but also considers himself to be a philosopher.
Well, at least I consider I consider him to be on the philosophical end of physics.
In some circles, the philosophy of physics is not looked down upon, and then in some it is. And I'd say in most it is. Now, in your view, where do you stand? Like, what are the pros and cons of philosophy as applied to physics?
Well, I think if you study quantum theory, then there is an element of philosophy about it. I would say that Bell's theorem, which is a theorem in physics, has huge philosophical implications. So it's somehow hard to get away from. I think if we're doing quantum theory or gravity for that matter, I think we're definitely on the boundary of physics and philosophy. I'm not even sure that I would know how to tell you where physics ends and philosophy starts. Now, it's true that there was a time when, say, for example, the interpretations of quantum theory, which is on the philosophical end of physics, where that had a bad name. But I think that's no longer the case, in part because I think that we've been able to be a lot more precise about, and say more about possible interpretations of quantum mechanics, for example.